Now, we have been talking about a dashpot which is an element which we all the time consider in a vibratory system model connected to mass, and then on the mass free body diagram we replace the connection with the dashpot with a dissipating force Fd, and we said that this dissipating force is actually proportional to velocity, and the constant of proportionality that we use always is a damping coefficient. Okay. This damping coefficient, where is it coming from actually? So, if the dashpot is represented here, so in physical sense the dashpot is what? It's in a shock absorber also. The dashpot is like a piston moving back and forth in the cylinder with a viscous fluid around. So, there is a viscous fluid around this cylindrical cylinder outer surface. So, the fluid here is viscous in nature. So, it has dissipating force generated, and we would like to know in detail as to how what form of this C parameter, what expression, or how do I quantify this based on certain physical design. So, you might be aware that if a plate is separated by a viscous fluid, so if it is separated by this viscous fluid, and if there is an initial there is a velocity which is given to this this plate, okay, equal to let us say V, the shear stresses in the fluid film are going to resist that motion, okay. And through the Newton's law we all know that the shear stress in the fluid film is proportional to the rate of shear. So, dV or dV over dz, if z is the coordinate in the vertical direction. So, it represents the position across the thickness of this fluid film. The rate of shear and the shear stress are related through the coefficient which is the viscosity or coefficient of viscosity, right. Now, if this is your piston or a vibratory mass which is executing a vibratory motion in this direction, then the shear stress here tau in the fluid film at the interface of the piston or the mass and the fluid film, if at that point if you want to find out the shear stress, then it will be equal to F divided by the cross sectional area. So, if this plate which is separating the stationary surface, sorry, the fluid film is separating this surface from the fixed plate, then the area here which is in contact, if that area is given by A, the force which is encountered is going to be equal to mu times. Now, this dV by dz dz I can replace that for the shear stress at the interface here at this location, that of course will be equal to if the velocity of this mass, if it is equal to capital V, let us say, that velocity will be same here, okay. So, now this V divided by the total thickness of this fluid film. So, if this thickness is given by T, dV by dz is going to be V by T. Now, here the assumption here is that the gradient is given by V by T, and then there is a linear variation of the velocity from the stationary surface here to the moving surface at the top. So, dV by dz can be written as V by T, where V is the velocity at the interface between the mass and the fluid film here, which actually now gives me a relationship between the dissipating force, the force that resists the motion of the plate or the mass over the viscous fluid film, to be equal to A times mu over t, and this v, the velocity, is nothing but our x dot value. It is the instantaneous dissipating force related to the instantaneous velocity of this particular mass, which is separated from the stationary surface through the viscous fluid film. And so that gives me that the relation is quite similar to this. So therefore, if I compare the dissipating force that I typically write when I am writing the governing equation of motion or deriving the governing equation of motion using these forces in the free body diagram, then it is actually coming from this. So it tells me that the damping coefficient, this constant which I have been using, is actually now is given by A mu over T. Okay. Now let me come back to this piston cylinder system, which is actually the physical realization of the dashpot, where if you want to relate this to this piston cylinder assembly, then what is separating the moving part with the stationary part? Obviously, because the mass is connected at the end of this piston, and as the mass vibrates, the piston reciprocates inside the cylinder, and it is this fluid film that basically causes the dissipation of the vibratory energy, and that is through the fluid friction. So the frictional force will generate heat, and the heat will get dissipated. So this is the source of the dissipation of vibrational energy. So what would be the area in question? Obviously, the cylinder, the piston surface, outer surface of the piston is what is going to be. So that is this area, that is going to be the area in question. Okay. Now how much is that area? If the piston has a length of capital L, and if the piston has a diameter equal to capital D, then obviously this C will take the form of pi d L as the area times mu over T, which is the thickness of the fluid film. In this case, I might like to indicate the clearance between the piston outer surface and the cylinder inner surface. So delta, if it is considered as the clearance between the piston outer surface and cylinder inner surface, then in that case this C is actually going to be pi d capital L over delta, and of course multiplied by mu. Okay. So this is going to be the damping coefficient, which we have been using without really bothering to know as to where will it come from, right. Now how will it come from? That if this dashpot is designed, you will get to know what fluid that you are using for a dashpot. So some viscous oil will be filled up in this, and you will know what is the viscosity of that oil. So viscosity coefficient of viscosity will be known to you. So you know this particular parameter from the constructional details. You are dimensioning, you know what is the diameter, what is the length, and what is the clearance. Okay, clearance between the piston and the cylinder. All of these will give a specific damping coefficient value, and the value will be of course Newton second per meter. Okay, that is the unit of the damping coefficient. Now this mu, if it is replaced by mu into pi, the alternate expression here, instead of coefficient of viscosity, I can use dynamic viscosity sigma pi d L over delta into 10 raised to power minus 3, where sigma is the dynamic viscosity in centipoise, given in centipoise. So, the alternate expression here for C is going to be this, where sigma is the dynamic viscosity. All right. So, based on the fluid that is being used in the cylinder and the dimensions of this piston and the clearances, you can numerically find the value of C, and that is how this C is going to come into the expression, right. In practice, when we use polymeric material, so we know that there are engine mounts which are made of polymeric material. So, in that case, instead of viscous damping, we will figure out that the loss factor or structural damping coefficient are the parameters which are used there. The dissipation is through intermolecular friction, dissipation due to the heat generated due to intermolecular friction in the material as the material is cyclically stretched. Okay, that is how the heat or the vibration energy dissipation is going to happen in case of a structural material, and the parameter that quantifies that dissipation is the loss factor, which is whereas in the case of viscous damping it is the damping coefficient. Okay, this example of a typical vibratory system here. Now, I am taking an example of a lunar lander. Now, you are all aware that we have this Chandrayaan Yaan, which is bound to moon, and I am sure it is going to have a landing on the moon, and the lander vehicle which is going to land on the surface of the moon is shown here, which is going to land, and when it lands, it is going to land through these props, and then of course, once it lands, then the rover is going to roll out. But essentially, as this particular lander is about to touch down on the surface of the moon, these are the props touching down with the speed which is given by v. We are interested in figuring out that after it touches down on the ground, what is going to be the response, vibratory response of this lander after the touchdown. Okay. And obviously, as you notice, these are the members which are going to touch first, and they obviously look inclined to the vertical direction, and there are 4 of them at the 4 corners of this lander. So, if you make a simplified model of this entire lander, it looks like this. So, there is a central mass here, and the outriggers here, so or the props which are shown here, they definitely might have the springs and dashpot which characterize its property, and there are 4 of them at 4 corners. And so, we would like to now make a vibratory model of this lander. What we are basically going to assume that the CG is in the center here, so that all the props are equidistant from the mass, and of course, another assumption is that we are going to look at what is the vertical vibratory response after it has touched down on the surface. Now, what is given in the example is that these props are oriented 70 degrees to with the horizontal. So, this angle is 70 degrees, and if I now make a simple spring mass dashpot system. So, I have a lander mass, and then there are 4 springs and dashpot in parallel at the 4 corners. So, I am basically now supposed to get an equivalent spring and an equivalent dashpot, which is representing the entire support system here. So, Ce equivalent damping coefficient and equivalent stiffness of all the props is given by these Ke and Ce, and then the mass of the lander is m here. With this I would like to then see as to how I can generate the vibratory response given that the lander touches down at the speed of v. Okay. We also assume that when it is landing, these props are fully stretched outwards, and they are free, and they are not restrained by any sense. So, those are the assumptions with which we will explore how we can solve this problem. Okay, now this making a model is our first step, as we have seen that the physical system has to be first converted into a simplified model, and then we have to get a mathematical equation, an equation which governs the response, and that will tell us what is the vibratory response of the module of the lander. Okay, so let us see how we now obtain the value of the equivalent damping and equivalent stiffness of this particular system, isn't it? So, how do I find Ke? We all know that the spring which are in parallel, they can be simply added to generate an equivalent stiffness, right. So, if this is K1, this is K2, the equivalent spring is definitely going to be K1 plus K2. However, in this case what we are seeing is that the springs are not vertical, they are oriented at an angle. Now, we would like to because our response is in the vertical direction and the springs are inclined, we need to now figure out how do we take care of such situations where the springs are inclined. And it is definitely true that the inclined springs will have a effectively different stiffness in the direction of the motion here. So, let's assume that the spring is making certain angle. As a general case, I am going to show you how this works out to be like. Okay. So, this is your mass, and the mass moves with the displacement x. Okay. Now, the spring here is making an angle of alpha. Now, if it moves by a small displacement x, okay. So, let us see, if it moves with a displacement x and it shifts to this point, this small displacement in the mass will cause the spring which is currently here to get stretched to this point. But will that be the total stretch in the spring? Definitely not, because now if I show the new position of the spring stretched to this point, let me draw this little separately here. So, it is this distance which is x, okay, but the spring is really not stretching exactly with x value. The original, if I drop a perpendicular from here, and we now know that the original length of the spring, if it is capital X here, this is going to be capital X, and actually the spring will stretch by this distance. And if this is alpha, and then if we assume that x is a small amplitude, which is all the time is our underlying assumption, that we are all the time going to talk about small amplitude vibration assumption, right. With that, this angle can also be treated exactly, I mean is treated close to alpha, and hardly any variation in the angle here. So, then this becomes x cos alpha. Okay. So, the net, even if the mass moves linearly in the horizontal direction by a value x, the stretch in the spring is not x, but is equal to x cos alpha. All right. Now, if you look at this mass as a free body and look at what is going to be the force which is going to act on this mass to pull it back to its original equilibrium position, the force is not going to act in the horizontal direction because the spring is inclined. So, the stretched spring will try to pull it back, and the force which the spring will apply, that force is going to be proportional to the stretch, and that stretch is x cos alpha, and because the spring constant is k, the force which is going to act at the connection point with the mass is going to be k x cos alpha. All right. Now, that force, if we resolve and see its component on the horizontal direction. Okay. So, now let us assume that this angle alpha made by the spring with respect to horizontal, the component of that restoring force which is going to act along horizontal direction in which I have applied the displacement, that is obviously going to be f cos alpha, right, which actually is k x cos alpha okay, because f is k x cos alpha. Now, if I am basically replacing the original inclined spring by an equivalent spring which is oriented in the direction of the motion, which I would like to do because I am going to orient it in the direction of the vertical vibratory response of the lander, that equivalent spring has to have an appropriate expression in terms of the stiffness of the spring. Okay. The stiffness of this spring irrespective of its orientation is going to be k, because the coil spring will have its own stiffness which is based upon the coil diameter, the wire diameter, the pitch, and so on. So, that stiffness is known, but what is its effective stiffness in the direction of the vibratory motion, which is horizontal, or in this particular case vertical, will be given by Ke. Now, this Ke obviously is multiplied by x is going to be the force which is actually this force. Okay. So, Ke into x is the force, and that force here has to match, and therefore, this f I can replace as k x cos square alpha and is equal to Ke into x, which actually means that the effective stiffness for an inclined spring is going to be k cos square alpha. Okay. So, for getting the same displacement x, an equivalent spring stiffness Ke has to be equal to k cos square alpha. Okay. So, that is basically how we treat an inclined spring. Now, all these four springs are inclined. So, if we consider these inclined spring as an equivalent spring in the vertical direction, and then look at these four springs at four corners as having the stiffness, equivalent stiffness as Ke, then obviously the final stiffness for the lander is going to be 4 times Ke, assuming that all the props have the same stiffness characteristic. And on similar lines, it is straightforward to also write the total effective stiffness damping be equal to 4 times Ce, where again Ce is going to be C cos square alpha, because the way we have got this Ke expression on similar lines, you can show same thing applies for the damping coefficient. Now, with this we can finally show this mass, stiffness and damping model, single degree of freedom lander model, having their individual values given by these, and now the model is ready, because you can that the value of K is given by this, the value of C is given by this, and then the touchdown speed is also mentioned here, V is equal to 0.2 meters per second. So, if the touchdown speed is 0.2 meters per second, how this mass of the lander is going to vibrate after it has touched down. The lander mass is also given as 3000 kg. So, what you needed was what you needed to solve this problem is all now in place. How do you solve for the response? We all know that this is now going to be a spring mass dashpot vibratory system, single degree of freedom system, and once it touches down, assuming that nothing else is exciting it, it is the classic case of response to initial disturbance or initial conditions, which for which we have already derived and know the expression for the response, which is given by this cos omega dt minus phi I, and the expressions for capital X and phi I, they also are properly they are known because they are functions of zeta, x naught, v naught and omega n, right. Similarly, phi I is also function of all these parameters. So, the expressions are already known to you. You can find out what is the capital X value based on the values of x naught, v naught. The initial displacement, initial velocity is known. Zeta is known because you already have the effective stiffness effective damping coefficient known. In this particular case, the numeric value of C is known. Zeta is basically going to be C over Cc. Now, Cc is 2 m omega n. Okay. So, you can find out what is omega n. Omega n is square root of k over m. Now, this k is nothing but this value 4 times the effective stiffness. So, you can find out omega n, you can find out zeta, everything in this case is known. The only thing that you need to understand that the value of initial conditions. What are initial conditions here? The lander is coming down with some velocity. So, that velocity is your initial velocity as it touches down on the surface. So, supposing that touchdown velocity is 0.2 meters per second, V naught is known. How about x naught? Is this x naught known? Is it 0? Now, you may notice here that when it touches down, we have assumed that these props are fully stretched out, right. That means they are not compressed. So, the springs in the props are outstretched and the mass is sitting here. Okay. So, it is still to touch on the ground, right. So, when it is not touching the ground, we are assuming here that these are fully stretched. The moment it touches down and the mass exerts its weight on the spring on all the 4 props, there is going to be a shift in the position of the mass, and that if you remember, we mentioned that as the static deflection. The deflection delta will get will have a value which is given by mg over the effective stiffness. Now, if I call this effective stiffness as K effective, then this K effective is going to be influence the value of static deflection of this lander mass. Of course, you need to take into account the appropriate value of g, because it is a lander on the moon surface. So, g needs to be appropriately taken. It cannot be 9.81, which is on the earth. So, essentially by knowing these values, you will be able to know with how much deflection the mass settles down at the mean equilibrium position. The subsequent vibration is going to happen around that mean equilibrium position. Okay. So, this is important that once it touches down, the vibration is going to happen around the mean equilibrium position after it touches down, which actually means that my initial condition x naught will be actually mg over k effective. Okay. And because just at the time of touching down, the springs are fully stretched out, and then it will depress or deflect to mean equilibrium position. So, initial conditions are not only touchdown velocity, but also the unstretched part of the spring. After the landing is complete and assuming that it does not bounce back, the motion is going to be around the mean equilibrium position, which is given by mg over k effective. Okay. So, this is the k effective that you have, which is equal to 4 times the equivalent prop stiffness considering the inclination of course, the inclination, the angle alpha that you are going to use here, that alpha angle will not be 70 degrees, it is going to be 20 degrees, because that is the angle it makes with the direction of the motion. 70 degrees are with horizontal, but the motion is vertical. So, it is going to be 20 degrees. That is how all the parameters of this response equation are now known, and then you can find out the response x of t as the lander lands on the surface. So, obviously, because it is a damped case, the amplitudes are going to decay depending upon the value of the damping factor, and therefore, you need to find out how this amplitude time history is to be obtained. What is the relevance of this exercise? I as a designer would like to know, now this is important, I would like to know what is the peak response amplitude which is expected if it touches down at 0.2 meters per second. If this amplitude after touchdown is larger than what a prop stiffness can handle, for example, if it is a coil spring and if it becomes solid, then you can have very large forces getting transmitted, and so basically based on the constructional details of the prop, I might use this information that I generate through this exercise as to find out whether these props are properly designed to take up so much of amplitude of motion. Of course, the amplitude is going to be the encountered only once, and based on the damping the amplitude will decay gradually. Okay. But this first peak is going to be important from the design perspective of the props. So, how do I use this response that I get finally? As you recall, the entire vibration analysis has the first step, which is getting the physical system converted into a simplified vibratory model. The most challenging part, where which we have done here, the physical system was modeled like a simplified vibratory model, but not only that is important, but finally when you generate the response, how do you use that response and interpret the outcome from the design perspective. So, one example here could be to check whether this response which is generated after it touches down, whether it is acceptable, or should I reduce the touchdown speed, or let the touchdown speed be higher if it can take care of that touchdown speed. So, essentially to carefully calibrate the touchdown of this lander, I might use this response which I am getting or which I am calculating for the purpose of design iteration. Okay. This is how this problem can be solved. Okay. Now, with the viscous damping model, there are alternate damping models available. Usually it is common practice to start discussing damped vibration response with the viscous damping model. That means the dissipating force considered proportional to the vibrational velocity of the mass, and the proportionality constant treated or considered is the viscous damping coefficient. So, here the assumption is the dissipating force is equal to or is proportional to the velocity. So, it is given by the expression Cx dot. Again, for getting a solution, mathematical solution, C is assumed constant, which I told you long back is an assumption. In reality, C is not that, I mean is not essentially constant, it is but with some restrictive assumptions like the clearance between the two moving surfaces is separated by a viscous fluid, and the clearance is small enough so that the expressions follow the law, and then the parameter C can be considered constant. So, with that viscous damping force Fd is given by this Cx dot. The viscous damping is the first damping model that we have. The dissipative force, as you see, is modeled by Cx dot. Now, what we shall do immediately following this discussion is exploring other damping models, because in practice for mechanical systems other damping are equally prevalent, and they are very important to study. So, after we talk about the viscous damping, we shall have a look at other damping models as well. So, in case of viscous damping, as we plot the dissipating force versus the displacement, cyclically as the vibratory system oscillates, it dissipates an energy which is given by the area within this graph of the dissipating force versus displacement, right. So, for a pure viscous damping case, the path traced by the dissipating force with the displacement against displacement is given by this area, and if we find this area, we get the cyclic energy dissipation, right. So, how is this expression arrived at? If we consider the viscous damping, then we all know that we can first write the expression for the displacement by this x, let us say sin omega t, where omega is the frequency of oscillation, and we know that from this expression we can get an expression for the velocity. Let us say if I write this as capital X omega cos omega t, and of course, the dissipating force F d is C x dot, which if I substitute for x dot, this is going to be C into x omega cos omega t, right. That is your x dot. Now, x dot itself, if I want to now find out what is the area within this graph, I shall first find out what is the incremental energy dissipated for a small displacement dx, which is going to be F d into dx. F d is the dissipating force at any instant. So, F d dx is the energy dissipated, and if I replace this F d by C x dot, which is basically C x omega cos omega t, and dx, from this expression I get expression of dx, which is going to be x omega cos omega t dt. So, I replace the dx with that expression. So, dx if I replace as x omega cos omega t dt. So, that is how I replace this dx in this expression. Okay. So, if I want to find the total energy dissipated, that is W d, that W d is going to be the cyclic integral dW. Let us say, because we have got this in terms of time, the total time for one cycle is going to be 2 pi over omega. Okay. So, that is the period of one oscillation here, right. So, this total energy dissipated is going to be integral 0 to 2 pi over omega. I can write this as C x square omega square cos square omega t and dt, that is it. So, if I integrate this within the limits 0 to 2 pi by omega, it is quite straightforward to show that this turns out to be pi c omega x x square. Okay. And that is how the energy dissipated in a cycle for a viscous damping case can be shown to be this. You will wonder why are we doing I mean how this expression is useful for us, because we already have an expression for FD which we have been using in solving many of the problems in the past. So, the reason why this expression is useful is that in practice, if we measure the energy dissipated in a cycle from a practical vibratory system, we can equate that numerical or estimated or a measured area or energy dissipated in a cycle with this expression to find an equivalent damping coefficient C, because in reality the damping will not behave exactly like a viscous damping. So, many times it is a common practice to equate this energy dissipated to the actual energy dissipated of a practical vibratory system, and after comparing you can get a value for this C, which we then would call as an equivalent viscous damping coefficient. Okay. So, what we do is to find equivalent viscous damping coefficient by comparing the two expressions or energy values. The advantage then we get is we simply replace this equivalent viscous damping coefficient value in all the expressions that we have derived for a pure viscous damping case. So, we assume that the actual damping behaves almost like a viscous damping case, its numerical value is obtained from here, and then the solution process goes as per the viscous damping case. So, that gives us a reasonably accurate estimate of the vibration response. So, in that context, this expression of cyclic energy dissipation for a pure viscous damping case is relevant. We shall see that part shortly when we discuss the other types of damping. Okay. So, I hope this is clear that the expression for cyclic energy dissipation for a pure viscous damping is obtained as you see here. These can be implemented and can be seen in some civil structures, like for protecting them from earthquake excitations, and so their actual picture can be seen here. So, there are variety of places where these viscous dampers are can be used. Okay. Now, we did some tests ourselves in the lab. So, you can see a typical commercial damper which of course has a spring as well, and then internally in this particular cylinder the dashpot generates dissipating force. So, a typical way of characterizing that is to hold it in a machine to give it a cyclic motion. So, you can give it a cyclic motion and then the machine measures the force as well as displacement as the damper operates under those cyclic motions. Please make a note, previous slide also showed us how we used a harmonic motion to characterize that or find the energy expression. So, this is practical way of characterizing the damper. This jaw moves cyclically with a predetermined frequency and amplitude. Okay. So, both of them are simultaneously measured, and from that we plot force which is encountered by the dashpot with its displacement, and you may get force versus displacement diagram at a particular frequency. So, this dashpot was for example, if you want to test it at 2 hertz, 10 mm displacement. This is how the diagram looks like, and then the area within this diagram is actually indicative of the energy dissipated in a cycle. And as we discussed, if you equate this energy which you are measuring, this will come like a value. You will then equate this frequency is known with which you have moved the jaw, and the amplitude that you have given or set to this dashpot. So, all of these known, the value that you will get from this expression is an equivalent damping coefficient. Okay. So, in this particular case, of course, it is a pure viscous dashpot, but in some other cases you may have any member which is not a pure viscous may not generate a pure viscous damping. Then in that case, whatever damping coefficient that you get is going to be an equivalent viscous damping coefficient. The reason is this area or energy dissipated, we are equating it to the to this expression which is derived only for a pure viscous damping case. So, therefore, the damping that you get is going to be an equivalent viscous damping coefficient. Another example of a different damping model is hysteretic or a structural damping, also called as the material damping. So, you will find the application in more number of practical implementations than pure viscous damping case. So, this is more widely occurring damping in mechanical, aerospace or civil structures than the pure viscous damping case. So, this picture shows the bogie frame of one of the train, and you can notice here the wheels and the axle is separated using this elastomeric damper. Okay. So, that damper in a close view, if you can notice, looks like this. So, there are plates, metallic plates separated by elastomeric material pads, and then as the motion happens, the pads undergo friction, intermolecular friction. So, this hysteretic or material or structural damping generates dissipating force because of the energy dissipated because of the intermolecular friction, rather than due to the fluid friction separating the two moving bodies. So, how do we make a model for such cases, like the dissipating force that we have been writing as Cx dot for a pure viscous damping case, whether this will be valid or it should be modified. Now, obviously, if you look at a structural member and if we try to deflect it, there is no fluid friction involved in most of our mechanical structures. But for example, the spring and mass system, if you practically look at that spring mass system, if you disturb the spring mass system, most of you would have done that experiment during your dynamics of machinery lab, is that if we disturb this mass, it does not forever vibrate despite the fact that there is no formal dashpot that is attached, but it does, the amplitude of vibration does reduce to 0, and the reason for that is predominantly the intermolecular friction or structural dissipating forces set up inside the spring as it stretches and undergoes mechanical strain is actually responsible for dissipating or converting the energy of vibration to heat because of internal damping, right. So, that structural damping is the damping responsible for dissipation of vibration energy when there is no formal dashpot attached, notwithstanding any other kind of a damping. For example, if this connection point or if this connection point has some relative motion, then there will be some frictional damping also coming into picture, plus the mass, if it is moving with higher velocity, it will have aerodynamic damping. But if we separate out or focus only on the damping force provided because of the intermolecular friction forces set up within the body of the material, that damping is our structural damping. Now, obviously, this expression cannot be valid for that because C does not exist in that sense, right. So, what are we going to do is, supposing that we have a mass and there is this kind of a motion of this mass. So, if consider a small isolator or an engine mount, the picture of which I will probably show, it will come up in subsequent slides, and some engine mount which is made up of some polymeric material, if your mass is placed on top of it and if you disturb this mass, that mass will vibrate about this vertical axis in the lateral vibration case, right. Now, this is going to generate a damping force. So, there will be some dissipation of vibratory energy because of internal damping in the structural member here, and also the same unit or a same mount or an isolator is also going to be acting like a spring, because it will try, as this particular mount deflects laterally as the mass moves laterally, it is going to restore, or it is going to generate a restoring force to bring it back to its mean equilibrium position. So, the same mount acts both like a spring as well as a dashpot. So, it makes sense to write this the restoring force, I will write this as Fr. This restoring force Fr, which is generated as the mass tries to move given an initial disturbance. So, both the restoring force because of the springing action of the structural member, which is a mount, will generate a restoring force which is going to be Kx. X is the lateral displacement here, but because there is a dissipation also because of the internal damping or due to intermolecular friction within the material, it is going to generate some dissipating force, which we are assuming to be given by Cx dot. Now, Cx dot is reserved, as we see, for a viscous damping case. So, what we are going to do is to somehow get an appropriate expression for this C by comparing the energy dissipated in a cycle for a structural damping case or a hysteretic damping case. And we all know, we have seen that whenever a structure or a structural member is subjected to oscillating displacement, it undergoes stress versus strain variation given by this. So, it may be in the form of a stress strain diagram, and this loop we all know is known as the hysteretic loop, and the area within this loop is the energy dissipated in a cycle. Okay. Now, if we are in a position to quantify this as Wd, the energy dissipated in a cyclic motion, what we can do is we can equate this to pi c omega x square, which is the expression we have derived for a pure viscous damping case, and then we can extract an expression for C and use that C here, assuming that this quantifies whatever damping that we have in the structure. Now, it has been observed from experimental investigations that most structures, for most structures, this energy dissipated in a cycle is proportional to square of the amplitude. Okay. And that we can write as alpha x square, alpha being the constant of proportionality. This expression um, is valid for structural damping or hysteretic damping, where it has been observed that the energy dissipated in a cycle is proportional to square of the amplitude. Now, what we can do is, if that is the case for structural damping, we equate this energy dissipated in a cycle for a structural damping to the expression for viscous damping, so that we get an expression for an equivalent viscous damping coefficient, which we will plug in the expression for the restoring force. So, with this we can get an equivalent viscous damping coefficient. Why we are saying this as an equivalent viscous damping coefficient is because it is actually not a viscous damping, but for the sake of this mathematical expression, we are plugging this C expression into the restoring force expression. With that, we can definitely see that the expression for C equivalent turns out to be alpha over pi omega. Okay. So, that is the expression for a viscous damping coefficient, an equivalent viscous damping coefficient obtained by equating the energy dissipated in case of a hysteretic damping to the energy dissipated expression from the pure viscous damping case. Now, we can write the restoring force F r to be equal to K into x. Now, this x I will write as, I will assume that again we are assuming a harmonic response or a harmonic motion of the mass, which we can write as either x sin theta or x sin omega t, or you can always you can as well use a complex expression, or an expression for x of t in a complex form. So, capital X e to the power j omega t is similar to writing x cos omega t minus phi or that. So, this expression is the assumed harmonic motion of the mass as it is perturbed, and I can write x dot from this by writing this as x j x omega e to the power j omega t, right. Now, with those two expressions I can write F r to be k x e to the power j omega t plus this C is now going to be replaced with an equivalent viscous damping coefficient. So, it is going to be alpha over pi omega, and then x dot will be j omega capital X e to the power j omega t. Okay. Now, with this what we get is, if I take k out from this expression, k is our stiffness coefficient of the structure, which you can find out, 1 plus j, maybe I will replace all these parameters clubbing into a parameter called beta x e to the power j omega t, where this beta is going to be what, alpha over pi into k. You can check that rest of the parameters are all accounted for. This b is beta, which I am writing here, is called as the loss coefficient. But if you now just compare this restoring force to the typical restoring force of a structure which we consider, the restoring force typically we know for any displacement is going to be k into x. Now, here the same way we can write as k tilde e to the power x j omega t, or I can write this as k tilde x of t, right, because this is nothing but x of t, and this I will club as, or I will call this as K tilde, where K tilde you can very clearly notice from this expression that it is now turning out to be a complex stiffness, right. So, the stiffness which we are getting in the structural damping case is a complex stiffness. You can see that there is a real part and then there is an imaginary part associated. So, this is the complex stiffness that we get uh, from the derivation that we have done here. That complex stiffness is a very peculiar character of the hysteretic or material damping, and the quantification of this complex stiffness is also through the loss coefficient which we have proposed here, which is dependent on the proportionality constant alpha, which you can find out. So, let us look at all of these. So, the damping that you generate through the structural damping case is through energy dissipated due to intermolecular friction. Of course, we have derived this expression by assuming harmonic motion. So, it is valid for harmonic excitation case. Energy dissipation for hysteretic damping is proportional to square of the amplitude. So, therefore, we wrote it as alpha x square, and therefore, C equivalent has been obtained by this expression, and then when we combine these two, we could write it, and finally, the expression that we got is complex stiffness times the displacement, and beta is the loss factor or a structural damping factor, and if we substitute for this alpha in the expression of omega d, that is the energy dissipated in a cycle, if we substitute for that for alpha, you get the expression for energy dissipated in a cycle in terms of the loss factor beta, right. So, many times in many of the commercial softwares where you can carry out some vibratory response analysis, it is common practice to specify in the analysis module the damping characteristic that you would like to analyze it with, and in that case the loss factor or a structural damping factor is the parameter that is typically asked, and that value which you supply is going to be this structural damping factor, okay. And with that it evaluates the response, but the genesis is here, right. So, this is where the damping in the form of structural damping or a hysteretic damping is to be accounted for. So, the second type of common damping model that we have considered here is the structural damping model. We shall take some examples based on this little later, but let us now very briefly look at what is the third most common damping model. Now, obviously, if it is not a viscous damping, if it is not a hysteretic damping, you will get you have an alternate damping, that is the third type of damping, which is called as the Coulomb damping or a dry friction damping. But I think before we do that, another small example of structural damping is the actual measurement that we did in the lab of characterizing this kind of engine mount. You can notice that there is an outer cylinder made up of some aluminum alloy, and then at the center you have the metal piece which you can see here, and between these two structural members, the internal cavity is all filled with elastomeric material, the rubbery polymeric material. That is basically is the material which is responsible for the dissipation of vibratory energy. So, if you actually test it again this was tested in the similar kind of a machine for its load deflection character, and you can see that there is of course a very small area in a cycle which is indicative of the damping in the system. So, this is a typical way in which you characterize for its damping property the mount as well as its stiffness. If you take the mean value and find out the slope of it, that is going to characterize for its stiffness value, and the area bound by the loop gives you a measure of the damping in the system. So, you can find out the structural damping factor or a loss factor from this graph and then use it for further analysis. Larger this loop area, more is going to be the damping and so on, right. So, that is how you can characterize. So, these are the recall questions. Kindly attempt these questions, very simple ones based on what topics discussed in today's lecture, and you can cross check your answers with those given in the next slide. So, the summary of lecture number 6 is that we continued our discussions on the various damping models. So, the initial part was of course the viscous damping. By default we discussed the response of a vibratory system considering viscous damping, but in this particular lecture we looked at the energy dissipated in a cycle for a viscous damping case, and then how this viscous damping is quantified through cyclic energy dissipated, and how it can be relevant when the actual damping in the system is not pure viscous. Okay. So, then we looked at the structural damping model in which is in fact most common de facto damping that you will always find in most of mechanical, civil and aerospace structures. So, the structural damping was discussed in detail, the concept of complex stiffness was introduced, and a structural damping factor or a loss factor was also introduced to you, and that basically completes two of the major damping models